The next trend here is ionization energy. Ionization energy is a test for how tightly electrons or atoms hold on to electrons. So if you read the definition here, it's how much energy I have to give an atom for it to give me an electron. And basically, it's the easiest electron to be taken. And what you can see here is it's measuring how tightly those electrons are bound. So if you really, really like your electrons, you're going to really tightly bond to them. If you're not so attached to them, it's going to be much easier for me to take them from you. And what you can see here is it's the exact opposite trend of our last one. You're small on the left. You're large on the right. Oops, sorry. And you are small on the bottom and large on the top. One thing you may want to write down, or you definitely want to write down, is noble gases have the largest ionization energy due to their stability. So they are stable. They have exactly the right amount of electrons, so they do not want to give any up to you. So, I mean, they're a pretty easy one to indicate there, but they're definitely going to have the largest one. You can see here on our picture, you can definitely see the noble gases are the highest family, and you can see as we go up a family, we do get larger, and as we go across, generally, again, we're on a trend here, but generally we are getting larger. So this one, we're looking for big guys up and to the right, and we're looking for small ones down and to the left. Let's move this so maybe people can see. Metals typically have low ionization energy because they do not tightly hold on to their electrons. They're not it's easier for them to lose them. Non-metals typically have higher ionization energy because they do bond to their electrons a little more strategically and strongly. What you'll see down here are called successive ionization energies. You are responsible for knowing this, and you do need to understand it. This is showing you your first ionization energy. So I'll write that down here. This is our first ionization energy equation. So basically I have an atom. I give it energy. It becomes +1, and I get an electron. And that's typically what we look at. When we talk about ionization energy, that's really where we're focusing. However, you can keep going. So this second one here is our second ionization energy. And again, what you're seeing here is we now are +1. We're giving it more energy. It's becoming +2, and we get another electron. And again, theoretically here, you can keep going. So down here, we have our third ionization energy. And I mean, theoretically, if you have unlimited electron or energy, you can keep going. Each time, you're going to get an electron. Every time you remove an electron, it does get more and more difficult. So your first ionization energy is the easiest. Second ionization energy is harder, so on and so forth. And one thing that's pretty cool is your ionization energies kind of directly relate to your charges. So if you look here, sodium has one electron that is kind of willing to give up. It doesn't hold it very tightly. So if you look, sodium's first ionization energy is very low, and that means it's very easy to take. But sodium only wants to give one electron away. So his second electron is very tightly bound. And what you can see here is there's a huge jump between ionization energy 1 and ionization energy 2. And basically, it's like sodium saying stop. It's saying, like, I don't want to do this anymore. Don't take another electron. If you look at magnesium, magnesium's typically +2 because it has 2 loosely bound electrons. And you can see his first ionization energy is, pretty low. Second ionization energy more, but not ridiculous. And then that's kind of all magnesium has. So you can see his third one gets very high. So it's kind of interesting if you look at these, what you look for is you kind of look for a real big jump. So if we look down here at silicon, we go from 787 to 1575 to 3000 to 4,000 to 16,000. That's a big difference. So that's kind of where the stop sign goes up. And what that means for silicon is he is willing to give up 1, 2, 3, 4 electrons. And that means he would typically be +4. So it's a cool connection that not everything has.